So the best way to understand paired tests better is to have a look at an example. So we have here the case where two drugs aiming at reduction of heart rate were used on 40 subjects. And now we have a graph where we represent the effect of the old and new drug on the particular patients. And now note the variability between the patients. So as we have discussed with the theory, different drugs may have different effects on the patients. So for instance, just for comparing two different patients, like the last one and then the four from the end, they have so differently responded to two different drugs. So that's why in cases like this, paired testing is more appropriate. So the question in this problem is it safe to say that the new treatment's effect differs from the old one? We don't ask is it better or worse, we just ask whether it differs. So it's a two-sided test verifying whether the difference between the two treatments is zero. And then we ask what is the 99% confidence interval for the difference. So let's go straight to MATLAB, where I have already the data ready. So I have my x and y vectors, which contain the two treatments for the same patients. We have 40 patients, so we collect their indices here. Then, of course, we do basic plotting. So we have the figure, which represents the bars. That's exactly the one we saw in the slide. And then we move on to the testing. So we calculate the series of differences, old minus new. Z is x minus y. And then, of course, n is length of that z, since we have equal number of patients, because they are the same patients. So the n in our test is just length of that vector. So since we are asking, is there any difference between two treatments? Our null hypothesis tests whether mean value of our z vector is 0 versus that it is not 0 on either side. Standard error, since it's a one sample problem, it's basically standard deviation of our z vector, but rescaled by square root of sample size. And then we calculate t-statistic. Since we are not told anything about the variance, we assume that the variance is unknown, so that's why we use t-procedure. So the t-statistic is basically the difference between the mean values and divided by standard error. And then we calculate p-value. So let's run this code and see what was the t-statistic first. So we have t equal minus 4.5016. So that's why, since we know it is on the left-hand side, if you think of t-distribution, so that means that we are in here, somewhere here far, minus 4.5. So that's why calculation of p-value means that we are just taking t-CDF rather than 1 minus t-CDF, because we know that t-value is negative, so we need exactly that small part on that side. And since it's a two-sided test, so of course that's why it is made twice. So it's 2 times t-CDF tn minus 1. Alternatively, if you want to have a code which works universally for any t statistic calculated, what you can do is then use the absolute value. So in this case, it would be 1 minus t-CDF of absolute value of our t. So if you don't want to check first, is your t positive or negative, just use absolute value in the formula here. And so that means that you will always be here on the right hand side. So that's why the p-value in here means that you need the CDF for this point, but 1 minus, because CDF represents that entire probability on the left, and we are only interested on the part on the right hand side. That's why it's 1 minus probability that any statistic can be less than t. Okay, and in this case, these two would return the same result. So now, since we get p-value smaller than 0.01, that means that there is very strong evidence to reject null hypothesis. So in other words, there is enough evidence to say that the new drug has a different effect from the standard drug. And then we were also asked about the confidence interval. So we wanted to know with 99% what is the confidence interval for that difference. So we basically calculate it like the one sample confidence interval. So we take the mean value of our z vector and then we make it plus minus the critical value from the t distribution. Since we need 99% confidence, it's a two-sided confidence interval. So that's why we take it for probability 0.995. And then the degrees of freedom, since again it's a one sample, it's just a sample size minus 1 and then multiplied by standard error. So from here, now we can see that z lower and z upper look like this. So now we could try to conclude more because we only asked about do they differ or not. And now we can see that the 99% confidence interval is on the negative side. We were taking the difference between old treatment and new treatment, and that difference is negative. So in our data, we were told that the drug was aiming at reduction of heart rate. So better treatment should be the one with lower values, but now it seems like statistically the new treatment has higher values. So we would say that the old treatment was better.